Thank you. Thank you. So I think you probably has heard several large language model presentation. This is yet another one. So people have been seeing a lot of applications, right? In the medical world, we were first shocked about how the model can perform. The GPT-4V actually can pass the US MLE test at 90, higher than many people can do. I mean, the passing score is 60, of course. And actually, I had a personal observation on this. So about 2 months ago, I organized a competition for high schoolers. So I printed this IQ test, asked them to do in half an hour. So the best can get like a 3 within half hour. Then I asked them to run a GPT model, just scanning and ask a GPT model to solve 0. It's too complicated. It's not directly solvable. And I say, okay, pair with the GPT model using whatever mechanism you want to use and then see how much you can solve. So within half hour, the best one girl actually achieved 8. Wow. So within 1 hour, you can imagine the IQ has doubled. Well, so my observation is these models are very powerful in the sense it has a huge amount of memory, right? It can memorize 128 kilobyte with less than a second. So way more than a human can do. In the context window, you can put in a lot of information for analyze. So humans still probably very good at making judgment, but memory, there's no way we can compete with this kind of model. However, can we trust them? Well, this is what I did 3 days ago. See, if you try today, I think it's still there. 3 models, right? All come from ChatGPT. I'm using the enterprise version from UT Health. So ask the same question: how many R's are there in strawberry? And my girl said, "Daddy, check it." I said, the old version is correct, 3. GPT-4o says 2, and then GPT-4o mini says 0. Gee, which one should I trust? Why? I think I just read the news saying they're going to fix that problem. The next version is coming in 2 weeks. Well, so not only it makes mistakes, it also fabricates things, right? That's even worse. In the literature, we probably already see there are attorneys using this kind of model to create evidence, and then he lost his license, right? And some students use this to write paper and then generate a reference that doesn't exist, right? So in my class, I ask a student, feel free to use it, but I will check the reference. Actually, sometimes they generate very nice reference, even in some reference of the colleagues I work with in their area, but the title just couldn't find. And then I ask them, is that paper you're currently working on? I submit to somewhere? I say, no, this is not my paper. Well, so let me talk about some of my ongoing research, and then I'll show you a few applications. So one of this work is in collaboration with the organizer, Dr. Xia, so led by his very talented student, Alan, on software prompting of calibration. So this is actually a very big issue in medicine. So people think what this model can do. The first thought is summary, right? I have a very lengthy medical report. I want to summarize it. What's going on? What's wrong? Can you trust it? See, just simple question. I ask which team plays in which stadium, right? Twice, almost the same question. First time correct, second time wrong. Well, this is just like a general question, right? What if in medicine, right? Look at this radiology report. So the patient actually doesn't have a pneumothorax indication, where it mentions all kinds of information related to chest and other things. And then the model actually gets misled. I think almost the same question. The first time, it shows the pleural airway with new pneumothorax. And the second time you run almost the same question. You ask, based on the clinical notes, give me a concise overview of the diagnosis, treatment plan, and the prognosis. It actually generates something that doesn't exist, right? Pleural opacity concerning pneumonia, which was not evidenced or supported by any of these writing here. So why? Generative AI, there's always a chance of hallucination, right? There's no guarantee its generation is faithful. So this is a problem you can only reduce but never mitigate. So what we came up with is a method to significantly reduce the chance of hallucination. So how to reduce hallucination? So the source of hallucination, when we look at it, is oftentimes because of the question you're asking. If you ask a too general question, then you get very general answer, right? There's so many information about the patient. What are you asking, right? Summary of what, right? Summary of last time, summary of this time, summary of family history, summary of conditions you're interested. You are not specific, right? The model doesn't know what you are asking, right? Because you are not very specific. Like when you ask a superficial question, you get superficial answer. Same thing here happens. So you basically change the embedding space of the input clinical nodes that is far away from what the original input clinical nodes should be in the embedding space you feed into a pre-trained model. So when this happens, what can you do, right? Move them back, right? So what we do is like look at the original space and then add a softer prompt and say, okay, if that's far away, too far away, just drag them back, like just put another vector, say, okay, that's too far away. Well, like maybe you should stay more closer to the fact. The fact is the embedding generated by the input clinical nodes without prompt. Okay, using this mechanism, we did some experiment, this is published, and then we showed that you can significantly reduce this kind of hallucination, and you can do this on the fly. And you see like in the lung disease radiology report, if you don't have this mechanism, oftentimes it gets misled to heart failure. Because a lot of terminology and a lot of information are very similar. So now I try to impute things don't exist, right? But we do not want it to impute things do not exist. Here the task is to stay with the fact. So after using this mechanism, performance increase, right? You do not have these kind of things. Well, so that's just the observation. And you have to be very specific, and then you have to stay with your original inputs. And then if you're far away, you try to find some mechanism, either contextualize it or drag them back in the embedding space. That helps. Okay, so I'm talking about another very common use case. It's called name entity recognition. For the NLP people, you're probably all familiar with what this is, right? In old days, when I say old days, it's like 1 year ago. When people want to do this ancient problem of name entity recognition, what they do is they manually annotate hundreds of entities. Say, this is address, that is zip code, this is name. Now I train hundreds of these examples. Tell me what is what. Right? This is hard. I worked on some projects like on dental notes. I trained a model, works very well in UTLs. When I applied to San Francisco UCSF data, broke horribly. So what happened? Because it's right sentence in 2 paragraphs. Our notes are literally in 1 paragraph, just because of that. Right? It's the same content, but their style is different. They have a heading, we don't have a heading. Well, we never see this kind of notes. Doesn't work. Right? How can I train a local model that will work for another institute? Portability is always the pain, right? NLP people know that. So large language model actually came to salvage. So as we know, like this model has been seeing trillions of nodes, right? Trillions of texts. So almost anything you can say, you can talk, the semantic structure it has seen. So generalizability is not the issue. The issue is example. What is the right example to give it to so that it can extract the right information so that you can utilize, right? So here is going back to the original question I'm saying, you have to give a very good question. You have to ask the right question. Now it's like ask the right question is 50% of success. So how can we ask the right question in the medical domain to extract what you want? So we find there is a nice common ground. It's this medical ontology. So in most of the medical domain, like cancer, Alzheimer's disease, or Parkinson, people spend like decades to come up with a very compact, precise description of the key terms they are interested in. And they organize in such a beautiful manner, and later I will show you, in a structured, contextualized manner. This is ENCODE, one of the prominent ontology for cancer. It's called minimum cancer oncology data element. It just a few hundred elements with branches, and then you can see there's mainly 6 different branches: disease outcome, genomic treatment, patient assessment. It's a hierarchical structure, but it's not a tree. It's a graph because there are nodes connecting from tumor to human specimen. It's across 2 branches. What it has, it defines what each element is. It defines what its attributes should be: string, categorical, numerical, or set value, right? It defines what it is. It also has a relationship. It defines what's the relationship on these edges. So with this, now you can actually come up with a mega prompt. So you can ask all these questions at the same time. And then it's very contextualized because this is for cancer, right? And I know cancer report typically has these things. And then because these are the people who work on the daily cancer cases summarized. So you could expect many of their notes actually contains this information. And then the attention mechanism in the transformer actually will bring these weights up if you see some evidence. For example, if you see some demographic information like ID, name, age, ethnicity, gender, then the probability of seeing the rest of them will be higher. So attention will bring that higher. So you even across multiple sentences, the model keeps searching for email and phone. This is not the previous model like BERT and MATBERT will do because they only look at single sentence or across two sentences is very exhaustive. But for this kind of model, the context window is very long, right? It can go across 100-page of PDF, and then as long as they see evidence, they'll put higher weights to search for them. If there's zero evidence on genomic, then they don't put much weight until they see any evidence, right? And then once they see evidence, it's not sequential. They use them jointly. It's like when you see handwriting, you see TIO, and you see them jointly being recognized together. It's much better than you recognize each word separately because you don't write TTO or typically, right? You match to the suffix. But this is not enough, right? So we tried first to come up with a gigantic mega prompt to encode every single information we want, and then try to extract everything from the nodes. So out of the box, we compare like a local model and Azure OpenAI model, which is also HIPAA compliant. It's good, it's not bad, as you can get like out of the box like an 85% of accuracy on 105 category, which is pretty good. However, there's big issue of hallucination because many nodes only have like a 30 to 40% of the entity you are interested in. When you ask these questions that doesn't exist in the nodes, what will happen? Hallucination, right? It try to answer any question you want to ask. That they make up things, right? So intuitively, what we're saying, okay, then let's do like a breakfast, like treat this as a hierarchical structure. Or we will go through each branch. Say, if you don't have any treatment, then I will not ask any treatment information. If you don't have demographic, I don't ask any demographic information. So this is the second approach, the BFOP approach. Significantly improved the performance. It's like giving us at least a 5%, 6% up in terms of performance. However, there is still another issue. That issue is we will lose a branch if we made a mistake, right? See, if there is the size of the tumor, but the early judgment says there's no tumor information, then we'll lose it altogether. So there's no chance even to look at the nodes like 3 layers below. So then we come up with yet another approach called two-phase ontology parser. So this mechanism is trying to make a judgment on every single node all the way from the root to leaf, binary classification, questioning whether you have the existence or evidence of this node, considering its parent and the sibling. And then you get a set of binaries, right? And then you try to resolve the conflicts. And after you resolve the conflicts, you have subgraph. And that subgraph contains merely the question should ask, right? So it's not too much, it's not too less. It's just merely the question you should ask for that nodes. And so each node has a different subgraph. Why we do this first? Binary classification is the simplest in machine learning you can do, right? If you cannot do binary classification, forget about the rest of the more complicated ones. So we started with this first pass to generate a subgraph, and then utilize that subgraph to do the extraction. So the performance gets much better. So out of the box, we get 95% of accuracy. It's like now it's almost like a annotation free. There's no need to do any example. All you need is to define and then use this automated approach to extract, and now you can verify. And for this mechanism, we have been publishing to Hugging Face and also released our protocol to ITCR, which is one of the NCI standing web portal. So people are using it. We have been collaborating with 2 major groups on clinical trial and other usage. So this is another use. Now I'll give another very interesting recent work. I've been collaborating with Beth Israel group in Harvard. So this is a very interesting observation I had recently. So we have a task, and I'll show you. So the basic idea is we want to come up with a model to identify adverse side effect for pediatric patient. So it's a sophisticated one because there's so many instances on overdose, underdose, delayed administration. So we'll go through the guidelines, we do chart review. For a total duration of like 3 months, we have this meeting for every single week, 3 physicians and us, we go through the chart review. I don't get it. I don't know what they're trying to do. I say like each time you review the case seems to be completely new. There's no common narrative of what you're trying to do. Like if everything is corner case, then what machine learning can do for you, right? Each time you say something different, there's no something I can summarize or conclude or utilize. Until one day I say like, why don't I just put everything, right? All the cases, all the guidelines. Of course, this is not done by one pass through many rounds. I extracted all the rules. It's just like one-page PDF. And it's just this logic, first-order logic. And I showed to these physicians. I said, is that what you want me to do? They said, yes, almost the same. Like, but we just modify here and there, just a few things. So really? The 3 months I just spent with you is like this simple? Yeah, that's it. So then later I realized, well, it's not that simple, like, because they use these terminologies interchangeably when they speak to me, like administrator, right? It is a compound condition of 3 things with and or and a time dependency. When they talk, they don't say administrator, they say these things interchangeably, because for them, this is the language they mastered for decades, right? For me, I'm drinking milk. I learned that for 3 months, right? How could I communicate with them and understand immediately, right? So we're speaking English, we're not talking the same language, right? So now we need a common ground. This is a common ground. So they agreed, I agreed, and then next day, I came up with this protocol using Lean4, which is a mathematical theorem proof language. So now things become so clear. I don't even need to worry about all the lines below the first top 8, because the rest is mathematical proof. I just prove whether there is an ASE or not. And then the first 8 is to do name entity recognition on CPR duration in minute, heart rate in BPM, pulseless binary, and API administration in numeric in minutes. So all I need is to get these, right? If I get these correctly, so better trust me, because the rest has no stochasticness, it's proof, right? And then we run into this model, and we achieve like an accuracy of 96.08, much higher than what we can achieve ever before. There's sometimes they can still make a mistake, but the mistake is because the inability to extract the right information from the text. But the problem has significantly simplified, right? Now it's no longer a proof, like a problem for extraction. Now it's a mathematical problem of proof, right? This I think is what ChatGPT should do to solve that counting R issue, right? They shouldn't let language model to do counting. They should use a mathematical model to do counting, using function analysis to handle what function analysis should be done, not to use a language model as stochastic to do deterministic task, right? So, well, now let me show you a few applications we're doing. So in UT House, we are actually doing some pilot studies on how to use these AI models in practice. This is a model that we did a long time ago, about 6 months. I just show you what this achieves.
Well, from what you've told me, Cynthia, I think the problem might be gallstones now. Did you have any worries or concerns about what it might be?
Well, not really worries. I mean, I hoped it was just indigestion. But gallstones, doesn't that mean surgery?
It could be, yeah. It's likely.
Okay. You see, we're planning this big family trip soon, and I'd hate to ruin it for them. Is there anything I could do, like diet?
Sure. You can cut down on your fat intake, since fat can provoke the attacks. At some point, they may have to be removed, though, and we don't want it to go for too long before it becomes serious. But listen, it's not an emergency now. Maybe we can work around that family vacation. So tell me, where do you plan on going and for how long?
Oh, we'll be gone for 2 weeks. We're heading down to Mexico with the whole family on
Wonderful.
a resort on the Pacific coast.
Good.
Thank you for watching. So this one is automatic coding. Yeah. So basically the idea is with the voice recognition we can do the coding, but what it makes difference is we use the proof approach, right? So I don't want a human in the loop. If things can be proved, you don't need to look at. You only need to resolve things that are challenging. That's another model.
Me duele mucho la cabeza desde hace unos días. ¿Qué puedo hacer?
My head has been hurting a lot for a few days now. What can I do?
I understand you're having headaches. How long have you been experiencing?
Yeah, so this is a real-time translation. The real strength here is we can translate in a way that a sixth grader can understand. You can put a context and say translate in a way that a sixth grader can understand. So glioblastoma become brain tumor in Spanish instead of another terminology. But we find oftentimes this medical literacy is not just a language barrier, but the literacy barrier. We also have models for generating exams for refreshing the class. So you load a PDF or an arbitrary reading material. We generate these quiz exams. So a clinician can do some refreshing the classes so they can train themselves and we see where are their weaknesses to give them more. And so these are the ongoing stuff. And I would like to skip this, and then maybe some other interesting research. This is digital twin. We do automatic scanning of the body of people so that we can create like a one-to-one mapping, later use that to guide exercise and training. And now you see, this is one-to-one, this is digital twin, right? I take it literally word by word. So this is what we do for exercise at home. So you can follow a video and then seeing what has been done.
Once the app
then
loads,
our app
you will
will
press play.
trace, and then if you do it incorrectly, it
Go
will not
down.
be counted.
Start.
You have to
Two,
do in the
one.
intensity it was given,
One.
and then in
Selected as given
a given time.
exercises for
If
shoulder
you,
up.
for
Two.
example,
The markers
do not
are
follow
placed
the instruction,
anatomically.
do not
Start.
reach
Capture
180
the
degrees,
angle
that
of the
will not be
shoulder and the
counted.
elbow.
And we give
Per
a
the
large language
instructions,
model
the elbow
interface
should remain
for the
straight
physical
during this
therapist to
exercise.
create these
The parameters
personalized
of this
therapy, so
exercise
they
Go
don't
up.
have to write any
are
code.
for
Go
Just
down.
shoulder
convert to
to be
JSON and then
abducted
ask
at
JSON what
least
is this.
90 degrees.
After some
So
iteration,
you'll-
they can generate this model. We're not happy with the 2D, so we're now getting into the 3D. And this is in the $1 million equipment at UTMB. We benchmark with them using a single iPad. So now we have achieved like a near the same performance. Where measurement error is smaller than day-to-day variance. So with that, I think we can confidently use that at home because the measurement error is very small. Last but not least, this is the number 20 Aloha in the US, the first in the UT system on our 6th floor. So we just got this bot, and we actually made a lot of changes. We added LIDAR, we added a new better cell, we installed a GPU, a very powerful one, and our second robot is coming. It's a humanoid, so we'll teach them to shake hands.
Shake hands.
So this is how it was taught. So there's teleprompting, so the guy
Okay.
behind is doing this, and then if the movement is good, he will annotate this is a good one. He'll repeat 10 to 15 times, and it learns this function. With the camera and then the position, you will know. Yeah. All right. Thank you.
Thank you, Dr. Jiang. Questions?
Thank you. Very interesting talk. I had a question regarding the project where you are using Lean 4. So do you have an automated pipeline, like kind of like end-to-end from like what they are talking about, building that kind of like flow diagram, and then encoding that to Lean?
Well, the generation of the logic is semi-manual. Then when the logic is generated, then go to lean is almost automatic.
Okay, so I think, I think I saw a glimpse of a slide. I think you are using Lean Dojo, maybe.
Yeah.
Yeah. So on that, because Lean Dojo is completely trained on Lean Playground, like it's a feedback mechanism, right? What Amazon did. For mathematical, specifically for coding purposes, when we do formal verification, we have a certain aspects where we check. That's how we do the feedback mechanism in Lean Dojo. Since you are taking concepts, like literally flow diagram concepts, how is that Lean? How did you? I would say, how did you modify that mechanism to actually generate code, like the Lean code for you?
Well, the Lean code was just generated by GPT, and then we verify some corner cases to make sure that it stays with the domain, and we plug in. But the code is so simple; you can just manually look at it. You know it's correct, right? If we're talking about some more complicated logic, then probably we need to build in some verification, validation strategy. For here, it's just a demo, so I probably don't need Lean 4, for example. I just think a simple logic will do the same work.
Thank you. One other question. So the digital twin part you showed, the digital twin, where you copied somebody using SLAM. So you showed two parts. One is copying somebody just using mobile phone, using SLAM, right?
Yeah.
And then you showed another part, I think you were using Postnet or something similar to kind of detect hand gestures, movements, everything. Did you actually look at mapping that with the SLAM model? Because the mocap data you are getting from the very expensive equipment, that probably can be mapped to the SLAM model, right?
No. The one I showed you on the other hand is 3D model extraction. This is marker system. This is marker list system. So this one was done on the array of depth RGBD camera. This was done on a single iPad with LiDAR sensor and our extraction. So we are benchmarking these two. So what we want to do is, if I get your body scan digital twin in the summer, I can apply it in the winter because you're dressing bulky clothes. Then I don't know where your shoulder is, where your leg is, but I can apply your model I extracted early on, or where you wear these tighter clothes so that I can still use. And I can put your personal avatar, say you should raise your hand to this, now you're here, right? So I can give you some incentive where you should look like,
Good questions. Any other questions? All right. Thank you, Dr. Xiang.
Thank you.